Hello, good morning everyone. I thank the organizers for putting together this event and giving me this opportunity to speak about my work. Before I start my talk, let me give a quick disclaimer that what I'm about to present is a very broad strokes heuristic exposition of a technical subject. So my idea is to get to the punchline without worrying about the details of the formalism. So consequentially, I've included no formal definitions and no theorems at all. I'll only be discussing some fascinating ideas. So in that sense, it will be a uncharacteristic math talk. So let me get started. So as the title may suggest, I'm going to talk about deformations as understood by an algebraic geometer. So deformation theory is an area of algebraic geometry which deals with the local study of moduli spaces. Now what do I mean by that? Given a solution to an algebraic problem, deformation theory deals with the analysis of infinitesimal perturbations to that solution. So in that sense, you can think of deformation theory as connecting to perturbation theory or deformation quantization in physics, which you may be familiar with. So I'm going to describe the modern avatar of deformation theory as developed by Jacob Lurie. So in this framework, one can associate to any deformation of an object a certain symmetry or a certain action on that object. So that is the punchline of my talk, and the rest of the talk is my attempt to convince you all of this fact. So I'm going to introduce deformations. I'm going to give examples of objects, but I'll leave the categories part to your imagination. I won't be talking about that. This talk is based on my work with Pranav, right? So what is a deformation? And before that, what are we deforming? What are the objects? So let O be an object. You could think of an algebra viewed as a module over itself. What do I mean by that? Just as you can think of the real numbers as a one-dimensional real vector space and complex numbers as a one-dimensional complex vector space, you can think of any algebra as a module over itself. Or you could think of a manifold, you could think of a vector bundle, or you could think of your favorite topological quantum field theory. All these are examples of objects. Imagine that O is a function of a parameter t. So fix some object O, which will help you follow along the talk, and let's say make that a function of a parameter t. So for every value of t, you have an object O of t, which is of the same type as O. You can call this data a family parameterized by t. More generally, you can have a space of parameters B. Right? So for every point in the space is a list of parameters t1 to tn, and every such space will have a special point called the base point, which corresponds to setting the values of the parameters to 0. Now, this is your parameter space. And you can have a family parameterized by this base space, so that for every point in the space, there is an object O of t1 to tn, which is of the same type as O, the object we have fixed. Now, a deformation of O is a family over the base B. So a deformation of the object O over the base B is a family parameterized like this by B, such that the object corresponding to the base point B0 is the object you're trying to deform. So that is what I'm calling a deformation. Just to say that again, a deformation of an object O over the base point over the base B is a data of a family over B such that the member of the family corresponding to the base point B0 is O. So you should mentally have a picture of a space, a map of spaces. Topological spaces or manifolds, whatever. This is your space B. This is the total space, and there's a map like this. And for every point here, the inverse image is the object O of t. You should be mentally thinking of it like that. So having said that, let me make a small digression and make an observation which relates families, as in things like this, to symmetries or certain actions. It's kind of well known that given a covering space, one can associate to it a certain action of the fundamental group of the base on the fibers. It's called deck transformations. On the other hand, given a certain group acting on a space, one can form a certain some quotient of this action, which gives us a fibration. So for those of you who are not familiar with these words, let me give two quick examples. So first, symmetries from family. So given a family, what is a symmetry? So consider this map from real numbers to circle, which is the exponential map. Right? Given any real number x, send it to e power 2 pi root minus 1 times x. Right? That is the map here. And then we know the fundamental group of circle is integers. And inverse image of the point 1 on the circle is also equivalent to integers. Now, given any loop in the circle, one can look at the inverse image of that loop. Let's say such that the initial point of the loop maps to 0. So one can see that when we lift the loop, it will open up and move towards either 1 or -1, depending on the orientation of the loop. So that kind of gives us an action of the loops on the base, on the fiber, and one can show that this is just the addition of integers. So in this case, addition of integers is what is the symmetry. On the other hand, how to go back? Given a symmetry, given a group action, what is the family? I've just cooked up some example, you can cook up your own example. So let's say integers are acting on circle, and the action is an integer n acts on this point on the circle by sending it to this guy, this point, right? That is the action I've defined. Now there's an action of integers on real numbers given by just translation. Just translate any real number by some integer. That's the action of integers on real numbers. And there's an action of integers on circle, which I've told you just now. So there's an action on the product space R cross S1, which is cylinder. There's an action of the integers on the cylinder. Just take the quotient by that action, and I'm claiming that space will give you a fibration over the circle. Now this is some funny quotient I've defined. It's called homotopy quotient. It's not important, the details are not important, but I'll get back to this homotopy in a couple of slides. Right, so now I've told you that you should mentally think of deformations as families, right? So then you can naturally ask me, does this correspondence hold in the story I'm telling you, right? Does this hold for deformations? The answer is yes, it does hold, but we have to work in the paradigm of mathematics called homotopy mathematics. That is a paradigm in which I took that quotient. So to summarize in one sentence, homotopy mathematics says that equality is not good enough. You have to provide the data of how you identify the two objects. That's the summary of homotopical mathematics. And in this paradigm, we should morally think of loops as the data of an identification of a point with itself, right? So that's why I said symmetries of a point, aka loops. Right, so given any loop, you should think of it as a map from a loop point to itself, but there could be many loops. You could ask, are these two loops equal? But then I can't, according to this paradigm, two things are never equal. You have to tell me how to identify them. So there could be a homotopy between the two loops. You could move one onto the other continuously. You have to carry that data also. But then there could be different ways of identifying these homotopies, and you can see where this is going. This just keeps going on. So in the spirit of homotopical mathematics, we should really be looking at space of loops rather than the fundamental group. So I'm claiming the space of loops in B based at B0 is the algebra which acts on the fiber. So formally this loop algebra is called the causal dual. So and then the statement is, to any deformation of an object O over the base B, one can associate an action of the causal dual, morally thought of as a loop algebra of the base, on the object O. Although this association need not be an equivalence at all times. Now there are various ways, various versions to make this precise at different levels of generality and different settings, and this has been done by various people over the years. So you can interpret these actions as some kind of a generalized symmetry of the object O. Right, so now I've basically described that there is a map going from deformations to symmetries, and when made precise, this arrow will be a natural transformation. Now, if you don't know what a natural transformation, that's all right. Just know that there is an arrow which takes a deformation and spits out a symmetry of the object. Now, having hopefully been convinced of this, you may ask me, are there objects O such that the above map is an equivalence? I told you in general it is not an equivalence. But are there examples of objects where this is an equivalence? Or you may ask, given an object O, is there an example of a base B such that when you restrict this arrow to that base, we get an equivalence? Or you could also ask, if O is a topological quantum field theory, is there a way to physically interpret this arrow? But these are questions, I don't have a lot of time to talk about, so I'm going to conclude with that. Thank you. But I'm happy to chat afterwards. Thank you.
Thank you, Bhanu. Any questions you can ask him?
Hello. When is it an equivalence?
What?
When is it an equivalence?
When is it an equivalence? Okay.
I'm just giving more time to you.
Okay, I have to give a technical answer. So if you have an object in a K-linear category, one category, and there's a T structure such that it's bounded below, let's say, then you can show it's an equivalence. So it's some kind of a finiteness condition on the objects, some algebraic finiteness condition, which ensures that it's an equivalence always, the first one. The second one, again, if you have a K-linear category, not an object, the category itself, with some finiteness conditions on it, one can show that when the base is such that the causal dual is again some sort of a finite object, some compact object, you get an equivalence. I don't have a broad answer to this, so I'm sorry if people didn't follow, but I had to give a technical answer.
Okay, another question, sorry. So suppose we take a concrete example.
Yeah.
Say we have a field K, characteristic 0 if you like,
Yeah.
and you have moduli of curves, for example, over K.
Okay.
A curves of genus 1.
Yeah.
And let us take a compact object and look at the a deformation in the, so suppose K has an extension K prime,
Okay.
and we look at the or sub algebra K prime, okay, and sub field K prime, and we look at the action of the Galois group. So asymmetry is given by the action of the Galois group. So we don't.
Sorry, what? No. I'm talking about specific symmetry which is given by the action of the causal dual. So I don't understand how the Galois group will act here.
No, but it is an automorphism of the point,
but
right?
I'm talking about some specific symmetry which is given coming from the causal dual. So I don't exactly understand how the Galois group will act here. Do you get right?
So I was trying to come up with a counterexample kind of, and wanted to know how it works with the theorem. So we can construct two different.
Because I don't think people are going to follow. Let's chat afterwards, if that's okay.
Sure.
Yeah.
Thank you, Bhanu.